This is the third video in the lecture series Dynamic Econometrics. My name is Eiko van Vuren and today I'm going to talk about the dynamic panel data models. Well, in order to start these dynamic panel data models, let me first of all recall a couple of things that we already know from the previous videos. First of all, recall the linear panel data model, which has a yit at the left hand side, and the right hand side we have beta 0 plus xit beta 1 plus vi plus wit, where I is going to run from 1 till capital N and t is going to run from 1 till capital T. We do already know that under strict heterogeneity of the regressors, that means that wit is going to be uncorrelated to, first of all, vi, but not only vi, but also with respect to all the xi's, so xi1 till xit. Then at that moment in time, we do already know that fixed effects methods, so that means either the fixed effects estimator, also called the within estimator, or the first difference estimator, they then provide consistent estimators for beta 1, of course, also beta 0, even when vi is going to be correlated with all the, or at least any of the xi's from xi1 till xi capital T. Well, we do already know as well that at the moment that vi is actually uncorrelated to, well, xi up till xi capital T, well then we do also know that pooled ordinary squares is then also consistent even under the assumption of weak heterogeneity. Weak heterogeneity implies that, well, we still assume that wit, the error term, is going to be uncorrelated to vi, but wit then is only going to be uncorrelated to xi small t, so only with the xi of the current period. Well, this is all we already know, but now I would like to go on with respect to the dynamic panel data model. I'm going to consider here the dynamic panel data model without any regressors in order to make it not well, more difficult than strictly necessary. That means that we have at the left hand side yit, and at the right hand side we have now gamma yit minus 1 plus vi plus wit, where I again is going to run from 1 till capital N and t is going to run from 1 till capital T. Well, we should realize now that, well, this model of course looks a lot like the model that we had in the previous slide. Well, there is no constant term here, but well, that's actually a minor difference, not to make it more difficult than strictly necessary. But apart from that, we do see that the xit that we have over here is replaced by a yit minus 1 over here, and that means that well, the regressor that we're now going to include is actually nothing else as yit itself, but lagged one period. Well, this model is also referred to the autoregressive panel data model. So apart from the fact that we call this the dynamic panel data model, we also sometimes call this the autoregressive panel data model. And then the lagged endogenous regressor yit minus 1 describes the state dependence or persistence. In order to go on with the theory, it might be so good to first of all look at a couple of different examples. And the first example is that we are going to suppose that the yit that we have over here is going to be the so-called current wage. So for example, the hourly wage of a particular individual. It depends on the previous period's wage, because wage bargaining and wage adjustments are typically based on the worker's past wage, so yit minus 1 directly influences yit. At the moment that a particular worker is going to ask at the end of the year for a new wage, then his or her boss usually is going to, well, look at the wage that you have right now, and typically you get a certain percentage extra, depending of course also on how well you performed in the previous year. But that of course implies that the say current wage always has an impact on, say, the wage in the previous period always has an impact on the wage that you have right now. You should, however, realize that at the same time, some people consistently earn more because of time invariant individual characteristics. That means a higher level of this vi that we have over here. We can think of that as abilities, just some talents that make you, say, more productive and therefore having a higher wage, more in demand, in fact, with respect to your employer. And this is going to affect the wages in every period of time. You should realize that at the moment that you have a particular talent, then it doesn't only have an impact on your, say, current wage, but of course also on the wage that you had in previous periods. And this of course gives difficulties, because of the fact that what we would like to know is how important actually the previous period wage was with respect to the current wage. However, because of the fact that talents actually do have also an impact on the previous period's wage, that makes it of course very difficult to disentangle the impact of, say, the talents of a particular individual and, say, the previous period's wage, because of the fact that very talented individuals also have a, say, relatively high previous period's wage. So therefore this is essentially the challenge that we have as econometricians, and it immediately implies that we are going to have a problem that VI and YIT minus 1 are likely going to be correlated to each other. Well, and then in addition to that, we can also look at an example that we already have studied before, and that is the student grades. Let grade IT denote now the grade of student I in period T. We should realize that grades tend to depend on previous grades because of accumulated knowledge. So that implies that the grade in IT minus 1 influences the grade IT. Well, this is immediately clear, of course, at the moment that we are going to think about particular exams that are not identical to each other, but at least related to each other. Then at that moment in time, for example, at the moment that we're going to look at mathematics exams, well, you should realize that if you get a couple of tests with respect to mathematics, then of course at the moment that you need to have a test with respect to calculating extreme values, well, then it might be very interesting to already know, of course, at least may be very helpful to already know how to take first order derivatives. So that implies that the exam that you probably had before that was about taking first order derivatives generally is relevant to know what your grade is going to be with respect to taking extreme values. So therefore we can expect that what you have learned in the past is not only, say, important for the exam grades that you had in the past, but also with respect to, well, future exams. At the same time, we should realize that some students consistently perform better because of time invariant individual characteristics. Again, that actually implies that these individuals have a higher level of the VI that we have over here. That could be related to ability or motivation. Some people are just better in mathematics, and therefore, even in the case that they would not have had a very high grade in the past, they actually are going to, well, have probably good grades in the future because of the fact that they're simply good in mathematics. Take into account, of course, that people who are good in mathematics usually don't have bad grades in the past. And this is going to affect the grades in every period, but are not directly observed. Of course, what we could do is that we could even look at a more richer model that would also take into account the, say, study time of the students. So therefore what we again are going to get is grade IT at the left hand side. We're going to get at the right hand side gamma 0 plus gamma 1 times the grade IT minus 1, so the grade in the previous period, plus gamma t times the study time IT, so the study time, the time that you have been studying for the, say, this particular exam, plus VI plus WIT. Well, we do already know that most likely VI is going to be correlated to the study time. That is to say that at the moment that students decide how much they are going to study for a particular exam, they in fact take their, say, ability into account. But at the same time, you should also take into account that this talents that people have, VI that we have over here, is not only going to have an impact, of course, on the grade that you have today, but also on previous grades. So that implies that most likely VI is going to be correlated with both the grade in the previous period as well as the study time that we have right now. Let me now go back to the model that we already had, which has a YIT at the left hand side, and we have gamma YIT minus 1 plus VI plus WIT at the right hand side. Well, if this is going to be the correct model, then of course we also have that yit minus 1 is equal to gamma yit minus 2 plus vi plus wit minus 1. This is then just the function that we're going to have with respect to the lagged outcome. The only thing that I have done is that I, for example, have replaced here, well, t minus 1 by t minus 2, and of course here wit by wit minus 1. Well, then what we can do is that we can investigate whether there is any correlation between vi and yit minus 1 by investigating the mean of vi conditional on yit minus 1 equal to this little yit minus 1. That we can do first. And what we would like to investigate is whether vi and this yit minus 1, they could be correlated to each other. Well, then what we could do is that we can then simply substitute here the yit minus 1 from the right hand side that we have over here. So then we get that this is going to be equal to the mean of vi conditional on gamma yit minus 2 plus vi plus wit minus 1. Well, we should realize that this never can be equal to 0, and that is for the simple reason that we have a vi over here and a vi over there. So therefore vi can never be uncorrelated to vi itself. So that implies that because of the fact that yit minus 1 has in its definition actually vi itself, that means of course that vi cannot be uncorrelated to this yit minus 1. What does this mean? Well, this immediately means that pooled ordinary squares would be inconsistent. Running a regression of yit simply on yit minus 1, and then this is going to be our error term, well, this will always go wrong. And the reason behind that is because of the fact that then our error term, which includes of course vi, is going to be correlated to this yit minus 1. So that isn't possible. So implies that what we need to do is that we actually need to have fixed effects methods in order to estimate this parameter gamma that we have over here. Question of course arises, how are we going to do that? Well, let me then consider once again this model that we have. So yit is equal to gamma yit minus 1 plus vi plus wit. What we need at the moment that we would like to use either the fixed effects estimation method, the within estimator, or first difference estimators, then what we need of course is strict heterogeneity. And we do already know that strict heterogeneity implies that wit is going to be uncorrelated to vi and any of the xi's that we have over here, so running from xi1 till xi capital T. Well, this relationship that we have over here isn't therefore strict heterogeneity, but in order for strict heterogeneity to hold, of course, at least wit should be uncorrelated with any of the x's. Well, take into account that in our case, xit, in this model that we have over here at the right hand side, is of course yit minus 1. So therefore we should realize that we can replace the xit's here by yit minus 1. If we're going to do that correctly, then what we're going to get is yi1 up till yit minus 1. So then we're going to get this relationship that we have over here that must be equal to 0. I'll take into account then that, well, at the moment that we're going to look at this, then the first thing I can do is that I can rewrite this model a little bit. We can write then something with respect to wit. We have here wit. So therefore what I can do is that I can bring these two terms to the left hand side, right the other way around. And we find that wit is equal to yit minus gamma yit minus 1 minus vi. If I'm going to substitute this into this, say, equation that we've over here, we get then this equation over here. Then we have that mean of yit minus gamma yit minus 1 minus vi, condition on all the yi's that we have over here, must be equal to 0 in order for strict heterogeneity to hold. Well, this is problematic, and the reason behind that is because of the fact that we should take into account that, of course, within the yi's that we have over here, there must be both yit and yit minus 1. That is, in here, for any t that we're going to have, there must then be, say, a yit and a yit minus 1. But that means that, for example, a necessary condition for strict heterogeneity to hold, for this to be equal to 0, it must be the case that yit must be uncorrelated to yit itself. That's of course impossible. So there we should take into account that, well, we cannot assume strict exoneity in this case. But that's of course a drawback because of the fact that strict exoneity then rules out dynamics. We can never have a model like the one that we have over here, where we put yit here, yit minus 1 at the right hand side, and still assume strict exoneity. So therefore strict exoneity rules out dynamics, while the possibility of studying dynamics is one of the main advantages of panel data. We do of course know that there is an alternative to strict exoneity called weak exoneity. We also already know what that actually is because of the fact that that implies that WIT is still going to be uncorrelated to VI, but now it's only going to be uncorrelated to XIT. This is then XI small t. So that implies that WIT only is going to be uncorrelated to the XIT in the current period. Of course, again, I is going to run till capital N, and T is going to run from 1 till capital T. But we should realize that XIT in our case is equal, of course, to YIT minus 1. So therefore we can also write it like that. And that means that weak exoneity implies that WIT should be uncorrelated to YIT minus 1 as well as with respect to VI. We can show that weak exoneity holds using the following assumptions. First of all, WIT is going to be uncorrelated to VI. That makes sense, of course. Otherwise, this would never going to hold. But in addition to that, we are also going to assume that the process WIT is going to be serially uncorrelated. That means that the mean of WIT conditional on WIT minus k for k larger or equal to 1, that must be equal to 0, which means in the sense that WIT is not going to be correlated to WITs in previous periods. So that's essentially what we're going to assume over here. And then finally, the first observation, YIT, that is of course YI1, must be exogenous. That implies that it's going to be uncorrelated to WIT for t going to run from 1 to capital T and with respect to VI. In order to see that, well, what we can do is that we can then try to rewrite the left-hand side of this definition of weak exogeneity. If we're going to do that, then the first thing that we can take into account is that we can of course rewrite this YIT minus 1 a little bit, because of the fact that we do know that if YIT is equal to gamma YIT minus 1 plus VI plus WIT, well then of course YIT minus 1 is equal to gamma YIT minus 2 plus VI plus WIT minus 1. We can substitute this right hand side into there in order then to get then this relationship that we've over here. Now we have that the mean of WIT, well, we are going to have that conditional on gamma YIT minus 1 plus VI plus WIT minus 1 and this VI that we've over here. Of course we can go on and we can then also rewrite this YIT minus 2. You should realize that if YIT minus 1 is equal to gamma YIT minus 2 plus VI plus WIT minus 1, then of course YIT minus 2 is equal to gamma YIT minus V plus VI plus WIT minus 1. So I can substitute this now into there in order to get then gamma squared YIT minus C plus gamma VI plus gamma WIT minus 1 plus VI plus WIT minus 1. Well, of course I can go on. What I can do is that I can then rewrite YIT minus C as being equal to, of course, gamma YIT minus 4 plus VI plus WIT minus C. Then substitute it back into here, and I can go on and go on and go on. And if I do that, then, well, at the maximum, then what I'm going to get is the following. I'm going to get here gamma to the power t minus 2 multiplied by yi1 plus the sum over gamma to the power s's multiplied by vi. And then we get another sum from ss1 till t minus 2 of gamma to the power s minus 1 multiplied by wit minus s. Well, you should now realize that this wit that we have over here is then by assumption uncorrelated to all these terms that we have over here. That is not too difficult to see based on what we had at the previous slide, because first of all wit is of course uncorrelated to this vi. That is the first assumption that we have made in the previous slide. But that means, of course, that WIT is also going to be uncorrelated to this term that we have over here, because that actually only depends on this VI that we have over here. So therefore, that term over here is also uncorrelated to WIT. We should realize that also this WIT is going to be uncorrelated to this term over here, and that is by the assumption of serial uncorrelatedness of this process WIT. Since WIT, the process WIT, is serially uncorrelated, it's going to be uncorrelated to all these terms that we have over here by assumption. And then finally, the final assumption that we have is that WIT is uncorrelated to YI1. So therefore we should realize WIT is going to be uncorrelated to all these terms that we have over here, which means, of course, that this thing must be equal to 0. And that means, of course, that weak exoneity on these assumptions that we had in the previous slide should actually hold. When estimating dynamic panel data models, we usually take first differences to eliminate the fixed effects. That is a so-called first difference estimator. That implies that at the left-hand side we're going to get YIT minus 1. Well, YIT is of course equal to gamma YIT minus 1 plus VI plus WIT. In addition to that, we do already know as well that then YIT minus 1 is equal to gamma YIT minus 2 plus VI plus WIT minus 1. But we get here minus signs in front, of course, because of the fact that this we also have here a minus sign in front. Then the next thing we can do is that we can rewrite this a little bit. The VI's, of course, they're going to cancel to each other. And we can take here the gammas together, this gamma over here, as well as that gamma that we've over there, in order to get then in the end gamma YIT minus 1 minus YIT minus 2 plus WIT minus WIT minus 1. But then we can rewrite this a bit. First of all, we can use the definition of a delta, and that is that we can write this YIT minus YIT minus 1, we can write that as capital delta YIT. Well, then this, of course, becomes equal to capital delta YIT minus 1. And finally, this becomes equal to delta WIT. So we can write it in this simple format that we've over here. Well, fixed effects, or better to say first difference estimators, now try to estimate this relationship over here by using ordinary squares of this rewritten model we've over here, where of course VI is no longer there. That cannot be done in this case, for the simple reason that we can actually prove that this delta YIT minus 1 is going to be correlated to delta WIT. How can we prove that? Well, that can be done by looking at the mean of delta WIT conditional on the delta YIT minus 1. What is that? Well, first of all, we can rewrite again. This is by definition, of course, equal to the mean of WIT minus WIT minus 1, conditional YIT minus 1 minus YIT minus 2. But we can rewrite YIT minus 1 because of the fact that we can write as gamma YIT minus 2 plus VI plus WIT minus 1, as I have done over here. We can then, of course, take the YIT minus 1s here together. Then we get gamma minus 1 multiplied by YIT minus 2 plus VI plus WIT minus 1. But that was even not that necessary, because we immediately see that this thing over here cannot be equal to 0, simply because of the fact that we have a WIT minus 1 over here and we have 1 over there. So therefore, this term cannot be uncorrelated to that term that we have over there. That means that first difference estimation, the first difference estimator, is here biased and inconsistent. But we can try to do something about that. Take into account that what we have over here is that the regressor delta YIT minus 1 is going to be correlated to, the error term delta WIT. And we do already have methods in order to correct, of course, for heterogeneity, and that is instrumental variable estimation. In this case, we can also try to use an instrument. And it can actually be shown that, YIT minus 2, so the second leg, that can actually be used as a good instrument. What do we have to show in that particular case? Well, then we have to show that the covariance between delta WIT and YIT minus 1, that must be equal to 0. That means, of course, that our, instrument should be uncorrelated to the error term. That is usually the assumption or the condition that we have with respect to instrument exogeneity. Apart from instrument exogeneity, we also need to have that the instrument yit minus 2 must be relevant in this case. That means that, well, yit minus 2 should be correlated to the endogenous regressor delta yit minus 1. So that means that the covariance of delta yit minus 1 and yit minus 2, they should actually not be equal to 0. Let me start by looking at instrument exogeneity. We do already know that our model is equal to yit is gamma yit minus 1 plus vi plus wit. Well, if this is going to be our correct model, then of course we do also already know that yit minus 2, our instrument, is of course equal to gamma yit minus c plus vi plus wit minus 2. Well, then we do also know that under the assumption of no zero correlation in wit, that's an assumption that we still are going to make over here. Well, then of course delta wit, which is by definition equal to wit minus 2, is going to be uncorrelated to any of the w's with a date of t minus 2 and earlier. Of course, this wit is going to be uncorrelated by definition of the no zero correlation. It's going to be uncorrelated to wit minus 1, wit minus 2, wit minus c, etc. And this one that we have over here is going to be uncorrelated to wit minus 2, wit minus 3, wit minus 4, etc. So that implies that delta wit is going to be uncorrelated to wit minus 2, wit minus c, etc. Well, then what we can do then next is that we can then look at our covariance. Of course, we do have to show that this covariance, the covariance between, well, delta wit, so the error term that we had at the previous slide of this model over here, is going to be uncorrelated to, say, our instrument, which is equal to yit minus 2. So we have to prove that this thing that we have over here is equal to 0. Well, what we can do is that we can substitute, of course, into the right-hand side that we have over here. I can substitute this into there in order to then get this right-hand side of over here, the covariance of delta wit and gamma yit minus 3 plus vi plus wit minus 2. Of course, delta wit, well, implies wit minus wit minus 1 is going to be uncorrelated with vi. That is what weak exogeneity, of course, says. But in addition to that, we should also take into account that, well, this delta wit is also going to be uncorrelated to this wit minus 2 that we have over here, just by what I said over here. We do not yet know about yit minus c, but what we can do is that we can, of course, write yit minus c as being equal to gamma yit minus 4 plus vi plus wit minus c. If I'm going to substitute this into there, I'm now going to get all these terms over here. I get now gamma squared yit minus 4 plus gamma vi plus gamma yit minus c plus vi plus wit minus 2. Well, we should realize that this is one of the new terms, and of course delta wit is uncorrelated to any wit, well, with t being t minus 2 or earlier. So therefore delta wit is going to be uncorrelated to this wit minus 3. Well, of course you may still say like, well, it could still be correlated with this yit minus 4. By the way, of course, delta wit is also going to be uncorrelated to this new term that we have over here, for the simple reason that both wit and wit minus 1, they're uncorrelated to vi. But as I already said, it can still be the case that delta wit could be correlated with yit minus 4. But that's not going to happen, for the simple reason that, well, this yit minus 4 only has terms that are even dated further back in the past. So we're going to get here, of course, wit minus 4 if I'm going to substitute this into. So therefore we should realize that we, based on this, already can say that delta wit is not going to be correlated with any of these terms over here. So therefore, this, say, covariance term is equal to 0. And that means, of course, that this covariance term must be equal to 0. Hence, what we have here is an exogenous instrument. At least yit minus 2 is an exogenous instrument for our model. Now let's go on to instrument relevance. We have already proven instrument exogeneity of yit minus 2, but we still have to prove, in fact, instrument relevance. What we do already know is that our model is, of course, equal to yit is equal to gamma yit minus 1 plus vi plus wit. But we then also know that then, of course, yit minus 1 is equal to gamma yit minus 2 plus vi plus wit minus 1. Well, that implies that we can rewrite a little bit yit minus 1 minus yit minus 2 by substituting here the right hand side that we have over here for yit minus 1. And then what we're going to get is that we then are going to get gamma yit minus 2 plus vi plus wit minus 1 minus yit minus 2. What we can then do is that we can then take these yit minus 2 terms together in order to get gamma minus 1 times yit minus 2 plus vi plus wit minus 1. Well, then what we can do is that we can then consider our covariance. The covariance that we are interested in is the covariance between yit minus 2, that's our instrument, and our endogenous variable delta yit minus 1. We want to prove that our, say, instrument is relevant, so therefore it should be the case that it should be correlated with respect to our endogenous regressor delta yit minus 1, which implies that this covariance term should not be equal to 0. Well, what we can then do is that we can rewrite this a bit. First of all, we can write this as the covariance of yit minus 2 and yit minus 1 minus yit minus 2. Take into account that the only thing that I now have done is that I have rewritten delta yit minus 1 as yit minus 1 minus yit minus 2. And then what I can do next is that I can then substitute in here the right hand side for yit minus 1 minus yit minus 2 in order now to get this thing over here. And then using the rules with respect to covariances, what we can do is that we can now write this covariance as, first of all, the gamma minus 1 multiplied by the covariance of yit minus 2 and yit minus 2, plus, of course, the covariance of yit minus 2 and vi, plus the covariance of yit minus 2 and this wit minus 1 in order to get now all these terms that we've over here. Well, the first thing that you should realize is that we actually have already proven that yit minus 2 is uncorrelated to wit minus 1. That's essentially what we have already proven at the previous slide, and the reason behind that is because of the fact that yit minus 2 only depends on wit minus 2, and that, of course, by the assumption again of no serial correlation, wit minus 2 is uncorrelated to wit minus 1. So this term over here is equal to 0. However, this term over here is definitely not equal to 0, and that's for the simple reason that yit minus 2 is by definition related to vi, because of the fact that yit minus 2 is equal to, well, gamma yit minus 3 plus vi plus wit minus 2. And therefore you should realize that yit minus 2 must be correlated to vi, so this term over here definitely is not equal to 0. Well, that's of course also true for this term over here, because we should take into account that, well, this is actually nothing else as the variance of yit minus 2. And because of the fact that yit minus 2 is not deterministic, this must be strictly positive. So therefore we do see that this term is not equal to 0. This term is also not equal to 0. And we should take into account that they're definitely not going to, well, they're not equal to each other with a minus sign in front. So therefore they're not going to cancel to each other, which means, of course, that these two terms together, they are not equal to 0, which implies, of course, that this covariance term that we have over here is not going to be equal to 0, which means that we have here a relevant instrument of yit minus 2. Concluding from this, the variable yit minus 2 can be used as an instrumental variable for the first difference specification. That implies that we are now going to get a model not with just one equation, but we're going to get two equations. The first equation has at the left hand side delta yit, and the right hand side we get gamma delta yit minus 1 plus delta wit. We have already seen that this is essentially what we're going to get with respect to our standard first difference specification, but now we get an additional equation, namely delta yit minus 1 is equal to alpha yit minus 2 plus eit. And well, this actually can be used in order to estimate this model with respect to 2 states least squares. We do of course know that yit minus 2 is going to be uncorrelated to delta wit, as well as that it's going to be correlated to delta yit minus 1, and we can estimate this by 2 states least squares. This is actually what is done in an old Journal of Econometrics paper from 1982 by Anderson and Chow. They actually exactly suggest this thing that we have over here. And here the identifying assumption in order to be able to estimate this with respect to 2 states least squares is the lack of autocorrelation in WIT. So what we can conclude from the previous slides is that YIT minus 2 can be used as a good instrument in our, say, first difference estimation model. However, we should realize that it's not the only instrument that we can use in this respect. Actually, we can prove that all lagged values of weakly exogenous regressors can be used as instrumental variables. So that means that we can also use YIT minus C, YIT minus 4, etc. Well, for that we have to prove, of course, again that, well, we have instrument exogeneity. That means that what we have to prove is that the covariance between delta WIT, our error term, is going to be, well, uncorrelated to YIT minus K. So this covariance should be equal to 0 for K larger or equal to 2. Of course, if K is equal to 2, then we get just that the covariance of delta WIT and YIT minus 2 is going to be equal to 0. That's something that we have already proven, but we now want to prove that this is even the case for any kind of K larger or equal to 2. Well, we can rewrite, of course, this covariance a little bit, and we should realize that we can always write a covariance always as the mean of the product of these two arguments. So in our case, delta WIT and YIT minus K, minus, of course, the product of the means. So therefore, the product of, in our case, the mean of delta WIT, and that multiplied with the mean of YIT minus K. Now we should realize that this term that we have over here should be equal to 0. And the reason behind that is because of the fact that this is, of course, nothing else as the mean of WIT minus the mean of WIT minus 1. And both of them, they are equal to 0, which of course implies that this term is equal to 0. But that, of course, also implies that this whole term that we have over here is equal to 0. So we can also write it in this format that we have over here. Well, then the next thing we can do is that we can then write this as the mean of WIT minus WIT minus 1 multiplied by YIT minus K. And we can further rewrite this because of the fact that this is, of course, equal to the mean of WIT multiplied by YIT minus K minus the mean of WIT minus 1 multiplied by YIT minus K. And this thing that we have over here, we can directly realize that this must be equal to 0. And that's for the simple reason that, first of all, look at WIT. Well, when is WIT uncorrelated to YIT minus K? Well, take into account that YIT minus K is, of course, equal to gamma YIT minus K minus 1 plus VI plus WIT minus K. Well, we should realize that WIT is, of course, by the assumption of, weak exogeneity, always uncorrelated to this VI. Well, it's actually also uncorrelated to this one that we have over here because of the fact that that only gives us higher order terms. So therefore, we only have to then look at this WIT minus K. But definitely, WIT is uncorrelated to WIT minus K for K larger or equal to 2. well, actually WIT, under the assumption, of course, of no serial correlation, well, WIT is already uncorrelated to WIT minus 1. So definitely also uncorrelated to WIT minus 2, WIT minus 3, etc. But what about this term that we have over here? Well, here we have WIT minus 1. Well, and we do still know that, of course, that YIT minus K is equal to gamma YIT minus K minus 1 plus VI plus WIT minus K. Again, well, WIT minus 1 is definitely uncorrelated with VI. And it's also uncorrelated to YIT minus K minus 1 because of the fact that this is just a higher order term. So therefore, again, we have to focus on WIT minus K. But we should realize that, of course, WIT minus 1 is uncorrelated with WIT minus 2 due to, again, the assumption of no serial correlation. But then, of course, it's also uncorrelated to WIT minus, say, 3, WIT minus 4, etc. And that, of course, implies that WIT minus 1 is then also uncorrelated to YIT minus K, which implies that both these terms, they must be equal to 0. And that means, of course, that YIT minus K for K larger or equal to 2 is an exogenous instrument. However, we still also have to look at instrument relevance. That means in this case that we have to prove that for K larger or equal to 2, YIT minus K is going to be correlated to delta YIT minus 1, our, say, endogenous regressor. Well, that we can prove by looking at the mean of the product of these two things over here. If this is not equal to 0, then definitely YIT minus K is correlated to delta YIT minus 1. Well, then we should realize that, of course, we do have already that our first difference specification is equal to delta YIT is gamma delta YIT minus 1 plus delta WIT. This is the first difference specification. We have already looked at that a couple of times before, but that of course also implies that delta YIT minus 1 is equal to, well, gamma delta YIT minus 2 plus delta WYIT minus 1. So that implies that we can substitute this into there in order to get then the mean of YIT minus K multiplied by gamma delta YIT minus 2 plus delta WIT minus 1. Well, then the next thing we can do is that we can then substitute in delta WIT minus 2 because of the fact that delta YIT minus 2 is of course equal to gamma delta YIT minus C plus delta WIT minus 2. So therefore this substituting into there gives us then, well, the mean of YIT minus K multiplied by gamma squared delta YIT minus C plus gamma delta WIT minus 2 plus delta WIT minus 1. Well, we can go on, of course, because of the fact that we can also then substitute in delta YIT minus C, delta YIT minus 4, etc. If you're going to do that many times, then in the end what we're going to get is this term over here. We get the mean of YIT minus K multiplied by gamma to the power K minus 1 delta YIT minus K plus, well, this sum that we've over here, a sum from SS1 till K minus 1 of gamma to the power S minus 1 multiplied by delta WIT minus S. We can still rewrite this a bit. What I can do is that I can realize that we can, well, get rid of the parentheses, of course. Then we get the gamma to the power K minus 1 times the mean of YIT minus K and delta YIT minus K plus, of course, the mean of YIT minus K multiplied by this whole sum that we've over here. So then we get these two terms over here. I can still rewrite this a little bit because of the fact that I can write this, of course, as the mean of YIT minus K multiplied by YIT minus K minus, of course, the mean of YIT minus K multiplied by YIT minus K minus 1. So in the end, I'm going to get this thing over here. Of course, the first term is the mean of YIT minus K squared. Well, and then what we can realize is that this term over here, this term is definitely not equal to 0. but this term is also not equal to 0. And the reason behind that is because of the fact that we should take into account that this term is only equal to 0 if yit minus k is equal to yit minus k minus 1. Then these two terms are going to cancel each other. But we should take into account that that never will occur, of course. It's never the case that yit minus k and yit minus k, they're exactly equal to each other because of the fact that we do not have perfect multilinearity. And that of course implies that this, say, whole mean that we have over here is not equal to 0. And that of course implies that yit minus k and delta yit minus 1 for k larger or equal to 2, well, they are actually correlated to each other, which means that we have here also a relevant instrument for, say, yit minus k for k larger or equal to 2. Concluding from this, we can say that we have many different potential instruments just to estimate one particular parameter. So in that sense, we can do something much more general than using two-stage z-squares to estimate a dynamic panel data model. Instead of that, we could also use the generalized methods of moments, usually denoted by GMM, and I do know that you did already have GMM during Introductory to Econometrics. There is a paper by Ariano and Bond from 1991 that was published in the Review of Economic Studies, and they developed a GMM estimator for dynamic panel data models, which can generate a large number of moment conditions based on lagged variables. In that sense, consider once again the first difference specification. Delta yit is equal to gamma delta yit minus 1 plus delta wit. Now for I is 1 till n, capital N, and t is from t up till capital T. In this case, t because of the fact that we should take into account, of course, that otherwise this would not go well. So therefore the underlying idea of GMM is now to find instruments that we are going to note here by zit that satisfy the moment conditions, well, that the mean of zit multiplied by delta wit equal to 0, that actually has to hold. For again, of course, t equal to t up till capital T. So in our case, we do know that in the absence of autocorrelation in the error terms of wit, we can use as instruments these zit. We can include yi1 up till yit minus 2. Yit minus 2, of course, because of the fact that we do know that k actually should be larger or equal to 2. So therefore we can use yit minus 2, yit minus 3, yit minus 4, etc. Of course, all the way up till yi1 that we have then over here. Well, then we can once again look at our first difference specification, as we know that is equal to delta yit is equal to gamma delta yit minus 1 plus delta wit. We can rewrite this a bit. What I can do is that I can bring this to the left hand side and write it the other way around in order to get that delta wit is equal to delta yit minus gamma delta yit minus 1. Well, we did already have our, say, moment conditions. The mean of yit minus k multiplied by delta wit must be equal to 0 for t going from t up till capital T. But what we now can do is that we can then substitute this into there in order to get our moment condition that the mean of yit minus k multiplied by delta yit minus gamma delta yit minus 1 is going to be equal to 0. So essentially what we now want to do is that we would like to get or search for a gamma for which this actually holds. And we should again have that, of course, t should run from t to capital T, and k should run from 2 until t minus 1 because of the fact that we should take into account that if we are going to substitute then t into, for example, here we get yi0, and that is of course not possible. Well, that implies that what we're going to get is 1 plus 2 up till t minus 2 different moment conditions. That gives us, of course, t minus 2 multiplied by t minus 1 over 2 different moment conditions in order to estimate only one parameter gamma. Of course, if t is exactly, capital T is exactly equal to 3, which is the minimum that we can of course have, well then at that moment in time we have only one particular moment restriction to estimate this parameter gamma, of course. But if t is larger than capital T is larger than 3, then there is over-identification, because we have then more moment conditions than parameters. We have then more than one restriction in order to estimate this single parameter gamma. Now note that the 2-stage squares method of Anderson and Chow has only one restriction. Well, we should realize, of course, that we have in that particular situation only one particular instrument, and that is yit minus 2. And that implies that the only restriction that we're going to have is that the mean of yit minus 2 multiplied with delta wit, well, that must be equal to 0. So that implies that since delta wit can also be written as delta yit minus gamma delta yit minus 1, that we can actually also have this restriction that we have over here. And that implies the following moment estimator. We can use here the analogy principle. That means that we're not going to have an expectation, but we are going to have a summation. We're going to sum over all the observations that we have. So all these things that we have over here and divide by the number of observations, and that is in this case 1 divided by n multiplied by t minus 3. That must be equal to 0. We can rewrite this a bit. First thing that we can do is that we can realize that we can get rid of this term that we have over here, because of the fact that this should be equal to 0 anyways. So then we can also write it in this format that we have over here. And then we can get rid of the parentheses. We can multiply this one with that one that we've over here. And we can multiply, of course, yit minus 2 with this minus gamma hat times delta yit minus 1 in order to get rid of the parentheses. So then we get these two terms over here. Well, then the next thing that I can do is that I can write this as two different sums, of course. One sum of yit minus 2 and multiplied by delta yit minus, of course, gamma hat multiplied, of course, then by the sum over yit minus 2 and multiplied by delta yit minus 1. So then we get then this thing over here, and can bring then, of course, this term to the other side. And then finally, if I'm going to divide the left and the right hand side by this summation that we have over here, then we finally are going to get that the gamma hat is going to be equal to, well, the numerator that is over here divided by the denominator. And take into account that this is actually identical to the 2-stage squares estimator that we had from Anderson and Chow. However, we can look at the general case, and then of course we get many more, say, moment restrictions. First of all, at the moment that we're going to focus here on delta wit, well, we should realize that delta wit only has one moment restriction, because of the fact that we should always go back 2 or at least 2 legs backwards, and that means, of course, 3 minus 2, that is only equal to 1. So therefore we can only relate this now to yi1. So we get this moment restriction over here, the mean of yi1 multiplied by delta wit must be equal to 0. And if we substitute in the fact that delta wit is equal to delta yit minus gamma delta yi2, well, then we get this moment restriction that we've over here. But that's not the only one, of course, because we can also now focus on wi4 and take into account that delta wi4 actually has 2 moment restrictions. First of all, we can go 2 legs backwards, then we get 2, but we can even go 3 legs backwards. So, and then we get yi1. So we can look at the mean of yi1 multiplied with delta wi4, that must be equal to 0, but also the mean of yi2 multiplied with delta wi4, that one should also be equal to 0. Well, we can go all the way, and we can even here look at delta wi capital T. Also, all these things should actually be equal to 0. So that implies that we can also write this, in fact, in matrix notation. Of course, we can keep it like this, but this is a little long. It's better to write this in a matrix notation, and that implies that what we're going to get is the mean of zi transposed, where z is still to defined matrix multiplied with delta wi. Also, I'm going to say what delta wi is going to be. That's equal to the mean of, well, zi transposed another time multiplied by delta yi minus gamma delta yi minus 1. Also, this is all going to still to be defined. That must be equal to 0. Well, and then we should realize that then the matrix zi that we have over here, well, that one is a matrix with a lot of zeros, but along the diagonal we have non-zero elements, and this first row that we have over here is related to delta wi3 that only has y1, as we here have only one, say, restriction, but we can go on, of course, with respect to delta wi4. That one has two restrictions with respect to yi1 and yi2. So therefore we here get yi1 and yi2. And we can go all the way to, well, the final one, the delta wit, and that has restrictions from yi1 up till, of course, yi capital T minus 2. So in the end, we're going to get this matrix over here. Well, apart from that, we also have the following, say, vectors. First of all, we are going to have delta wi. Well, that's actually nothing else as a vector that starts here with delta wi3. Then we have delta wi4 up till delta wi capital T. And that's, of course, nothing else as, well, for example, here we have as first element delta yi3 minus gamma delta yi2. But we can also write delta wi as delta yi minus gamma delta yi minus 1, where yi is going to be simply equal to a vector that has as elements delta yi3 up till delta yit, and yi1 or minus 1, yi minus 1 is going to be equal to, well, delta yi2 instead of here delta yi3 up till delta yi capital T minus 1. Now that we have our matrix notation, what we can do is that we can now derive our, say, moment estimator, based, of course, on this moment restriction that we have over here. But what we then would like to do is that we would like to use another time the analogy principle. That means that we are going to have no, say, expectation, but we're going to have summation, and we're going to sum over all the observations that we have, and we divide by the number of observations that we have, and that is in this case equal to n. However, take into account that since we set that equal to 0 anyways, we could simply use this moment estimator over here. And that implies that in principle what we would like to do is that we would like to find a gamma hat in such a way that all these moment restrictions that we have over here are going to be satisfied. Take into account, by the way, that well, as this thing that we have over here is in fact nothing else as a vector of moment restrictions, that also holds true, of course, with respect to this thing that we have here at the left hand side. This is actually nothing else as a vector. It's therefore a system of equations, and the number of equations that we're going to have is equal to t minus 2 multiplied by t minus 1 over 2. So we should take into account that this thing that we have over here for any kind of t that we have over here, apart from, of course, the situation in which capital T is equal to 3, this will be strictly larger than 1. And take into account that we only have one particular unknown. The unknown that we have is gamma hat. And therefore we should take into account that even in the case that the moment restrictions are going to be correct, so even if these moment restrictions that we have over here are theoretically correct, and they are of course correct on the assumptions that I've made so far. Take into account that we have made a couple of different assumptions, for example that WIT is going to be uncorrelated to VI. In addition, that we have assumed that there is no serial correlation with respect to WIT, and finally we have assumed that the first observation of YI1 is going to be exogenous, so therefore also not correlated to WIT. These are the three main assumptions that we have made so far. And under these assumptions, you can actually quite easily show, and we have done that so far already, that these moment restrictions should actually be correct. However, even if they're going to be correct, we should take into account that generally we will not be able to find a gamma hat over here that will satisfy all these moment restrictions that we've over here. That is due to the randomness that we have with respect to the data. However, at the moment that n goes to infinity, well, then we do know that then at that moment in time, these things that we have here at the left hand side, they are going to converge towards the moment restrictions. So these moment restrictions that we have over here, and then of course the only solution that we are going to have then is that gamma hat should actually be equal to gamma. If n of course is going to go to infinity, then at that moment in time we are going to have that well, this moment restriction is going to be correct. But in the finite sample case, we will never be able to find a gamma hat that is going to, well, solve all the moment conditions that we have over here. So therefore what we're going to do instead is that we are going to intend to find a gamma hat that approximate the moment conditions as good as possible, even for finite samples. So instead of trying to find a gamma hat that will satisfy all the moment restrictions that we have here at the left hand side, we try to find a gamma hat that more or less is going to, well, get these things equal to zero. And that's the whole idea behind GMM. In GMM, we usually are going to introduce a criterion function, and that I'm going to note here by Keller graphic m gamma hat. And what is it? Well, it is first of all, here between the parentheses we have essentially nothing else as the left-hand side of the moment restrictions that we had at the previous slide. So these moment restrictions that we have over here. That is this thing over here. It's written a little bit differently because of the fact that I have used delta wi gamma hat for this delta yi minus gamma hat multiplied by delta yi minus 1. For that I have now used delta wi gamma hat, but it essentially is exactly the same. Well, we should realize, as I already said, that this is actually nothing else as a vector of all our moment restrictions. Well, we can of course transpose that and multiply that another time by the same vector. We get then the inner product. Well, we should realize that at the moment that n goes to infinity, then at that moment in time it is possible to satisfy all the moment restrictions, and that means of course that this vector that we've over here becomes a vector of zeros, and that one becomes a vector of zeros as well. Whenever we set gamma hat exactly equal to gamma, that is the correct value of gamma. We can only do that of course if n goes to infinity. Still, even in the case that n goes to infinity, we should realize that if we're going to choose another value for gamma hat, not equal to the real value of gamma, well then the criterion function is going to be positive because of the fact that an inner product always is equal to 0 or positive, of course. 0 in the case that all these moment restrictions are going to be equal to 0, and that is only possible at the moment that gamma hat is equal to gamma, and in all other cases this thing is going to be positive. So therefore what we're going to do now is that we're going to minimize this criterion function. So therefore gamma hat is going to be the argument that minimizes that criterion function. That means of course that if n goes to infinity, then there's only one solution to this minimization problem, and that is of course in which gamma hat is exactly equal to the true value of gamma. That means of course that we're going to get a consistent estimator. Well, that's the whole idea behind GMM estimation, but we should take into account that GMM estimation doesn't try to minimize this criterion function, but it uses a little bit of a different criterion function instead. Instead of just using the inner product as we had here at the previous slide, we're going to have here that, well, again, we are going to have our vector. We are going to transpose that vector, but we are going to multiply it then by a, say, symmetric weighing matrix. It's a positive, definite, and symmetric weighing matrix Wn. That's the thing that we've over here. And then we multiply it by, say, our vector of, say, left-hand sides of our moment restrictions. Now you should take into account that, well, the things that we have said at the previous slide still hold, and that implies that if n goes to infinity, and for finite at t, then we still are going to have, of course, that, well, there's then only one, say, minimum of this thing that we've over here, which, of course, is gamma itself, the true value of gamma. And that implies that for any kind of, say, positive, definite, and symmetric weighing matrix that we are going to use, we are going to get a consistent estimator for gamma, but they will actually be different. And these estimators are going to be different in terms of their asymptotic efficiency. Now, an important question that arises is, well, if we could use different values of Wn, the weighing matrix, which matrix should we then at that moment in time choose? Well, what we should realize is that the optimal weighing matrix always is going to minimize the asymptotic variance of the estimator. This implies that the optimal weighing matrix is proportional to the inverse of the covariance matrix of the sample moments. That means that our optimal weighing matrix, that I'm going to note here by Wn star, is going to be equal to this matrix that we have over here, which is the sum over CZI transposed times delta Wi times delta Wi transposed times Zi. We are going to sum that up and divide by the number of observations that we have, and we still have to take the inverse over here. Take into account that there is a nice intuition behind this. You should realize that sample moments with a small variance get more weight in this case, as these provide more accurate information about the parameters than sample moments with a very large variance. Take into account that at the moment that you have a sample moment that has a very large variance, well, why would you take that, say, sample moment a lot into account by estimating at the moment that you estimate gamma hat? Why would you try to get that one very close to zero at the moment that it actually does have a very large variance? So therefore, what you're going to do is that you're going to try to get, say, the moment restrictions that have a small variance, you try to get them very small and very close to zero, whereas the ones that have a large variance, well, they do not have that much of accurate information anyways, so they can be a little bit larger. That's the whole idea by taking the optimal weighing matrix. Now we should take into account that there is a problem. And the problem is that we should take into account that this optimal weighing matrix actually depends on delta Wi. And the delta Wi is unknown because of the fact that it actually depends on our unknown value of gamma hat. Take into account that if we go back over here, we actually already said that Wi dense or delta Wi does depend on gamma hat because of the fact that well, delta Wi is actually nothing else as this thing that we have here between parentheses. It's equal to delta Yi minus gamma hat times delta Yi minus 1. And take into account that there's now a problem. The problem that we have is that in order to estimate gamma hat, we are going to set the optimal weighing matrix, but then we are going to see that this optimal weighing matrix actually does depend on gamma hat. So that is actually problematic. So the question arises, how are we going to solve that problem? Well, in order to overcome this, we can proceed in two ways. Either we're going to impose some additional stochastic structure on WIT, or we could use a feasible two-step procedure. Well, let's start actually with the first one. Try to, well, add some additional stochastic structure on WIT. And more in particular, what I'm going to do is that I'm going to assume that WIT is homoscedastic. That's not necessarily the case, of course, but if WIT is homoscedastic, then that means that the variance of WIT conditional on any kind of YIT minus 1 is going to be equal to sigma squared. Well, then at that moment in time, it's possible to show that then the optimal weighing matrix W star n is going to reduce to sigma squared, the sigma squared that we have over there, multiplied by, well, actually nothing else as this simple matrix 1 over n multiplied by the sum from I is 1 till n of zi transpose times jn times zn. And take into account that, well, jn now replaces this part that we have over here. And therefore the question arises, what is that? What is that in the case that we do have, say, the assumption of homoscedasticity of WIT? I'll take into account that, well, what we are going to have is that we are going to have here a matrix. And along the diagonal elements, well, simply we're going to get the variance of WIT minus 1. We're going to get then the variance terms, of course, of this, well, WIT that we have over here. Delta WIT, of course. So what is that? Well, that's of course equal to the variance of WIT minus 1. We should realize that that's always equal to the variance of WIT plus the variance of WIT minus 1 minus 2 times the go variance of WIT and WIT minus 1. Take into account that this is actually always true. It's always the case that at the moment that we're going to look at the variance of a difference, that's always equal to the, well, the sum of the variances minus 2 times the covariance of the different terms that we're going to subtract from each other. Well, the question of course arises, what is this? Well, this last term that we have over here is of course equal to 0. And the reason behind that is because of the fact that we have assumed no zero correlation. And that means of course that WIT is not correlated to WIT minus 1. So therefore this term is equal to 0. But these two terms, they are actually equal to sigma squared under the assumption of homoscedasticity. So therefore this simply is going to be equal to 2 times sigma squared. Then we can also look at the elements here of this matrix just off the diagonal. Then we're going to get the covariance of delta WIT and delta WIT minus 1. That's of course equal to the covariance of WIT minus WIT minus 1 and WIT minus 1 and WIT minus 2. Well, that thing here is of course nothing else as the mean of WIT minus WIT minus 1 multiplied by WIT minus 1 minus WIT minus 2. If we are going to get rid of the parentheses over here, what we get then is the mean of WIT minus multiplied by WIT minus 1 minus the WIT minus 1 squared minus WIT times WIT minus 2 plus of course WIT minus 1 multiplied by WIT minus 2. You should realize that at the moment that we are going to get all these terms over here, then what we are going to get is that this term, for example, is equal to 0. The reason behind that is because of the fact that again there is no zero correlation, so therefore, well, WIT is not going to be correlated to WIT minus 1. The same is actually true for this term over here. WIT is also not correlated to WIT minus 2. But finally, of course, as well, WIT minus 1 is uncorrelated to WIT minus 2. So that means that also only this term actually is not equal to 0. So therefore we can write this as simply equal to minus the mean of WIT minus 1 squared. And take into account that this term over here is actually nothing else than the variance of WIT. So again, that is equal to sigma squared. Well, and then further off the diagonal, well, we should realize that it's then not that difficult to prove that then all the terms that we are going to have with respect to the covariance, they must be equal to 0. So therefore the final, say, Jn that we're going to have, take into account that we have already here a sigma squared in front, so these are these two sigma squareds that we have over here. Jn simply is equal to, well, it's a matrix with 2's along the diagonal, and off the diagonal we're going to have minus 1's over here. Well, that is just off the diagonal, and further away from the diagonal we simply are going to get zeros. take into account that the nice thing with respect to this is that this weighing matrix does no longer depend on delta Wi, and therefore we can actually directly calculate this Wn star without having to know this delta Wi, and without having to know gamma hat. We can directly calculate this and then of course do our, say, minimization with respect to GMM. However, there's also an alternative, and that's a two-step procedure. In a two-step procedure, we first are going to use the weighing matrix is replaced by the identity matrix, which provides an estimate of gamma hat that can then be used to actually, estimate delta Wi hat. Well, if we replace in the optimal weighing matrix then delta Wi by delta Wi hat, then we can obtain an estimate for the optimal weighing matrix. So in order to explain this, at the moment that we're going to use the identity matrix for the weighing matrix, then essentially we're not going to do anything else than minimizing this criterion function that we have over here without, say, our weighing matrix. Well, that will give us an estimator or an estimate of gamma hat, and that we can then actually use in order to calculate, an estimator of delta Wi, and then we can substitute in here in order to get then finally an estimator of, say, our weighing matrix, our optimal weighing matrix W star n. Well, that will give us then an estimator. What we could do as well is that we could, of course, also in the first step also use gamma hat, which is estimated under homoscedasticity. That's the estimator that we actually have derived over here. That is the one that was actually proposed by Ariano and Bond. And remember again, so we are able to estimate this with GMM, and the key assumption for consistency again of the GMM estimator is that there is no autocorrelation in WIT. I would like to go on to the next topic, and that is the topic of the problem of weak and many instruments. In order to start this topic, remember that we, of course, had this model that we have over here. We had YIT at the left-hand side, and on the right-hand side we have gamma YIT minus 1 plus VI plus WIT. Also, do remember that based on this model, we already have derived the following equation that we have over here, where we have delta YIT minus 1 at the left-hand side, and at the right-hand side we have gamma minus 1 times YIT minus 2 plus VI plus WIT minus 1. This is a thing that we have already derived, say, earlier during this lecture. Well, the nice thing with respect to this equation that we have over here is that it immediately shows the relationship between our, say, endogenous regressor, delta YIT minus 1, and a potential instrument, YIT minus 2, because of the fact that we do see that YIT minus 2 here is at the right-hand side of the equation of delta YIT minus 1. And therefore, it is a relevant instrument with respect to this endogenous regressor, delta YIT minus 1. But we do also see that this is actually our coefficient. It is equal to gamma minus 1. And because of the fact that we generally assume that gamma is in absolute values smaller than 1, that means that we rule out the unit root. That is for a reason that has already been discussed earlier during this lecture series. Well, therefore, we are going to see that the value that we have over here, gamma minus 1, is also in between, in absolute values, in between 0 and 1. And that, of course, implies that, there is a relationship over here, and, the relevance or the strongness actually does depend on the actual value of this gamma. However, what we can do as well is that we could then also substitute in here the value of YIT minus 2. We do know that YIT minus 2 is equal to gamma times YIT minus C plus VI plus WIT minus 1. If we're going to do that, then we're going to get this equation over here. Again, now we're going to see that now YIT minus C is at the right-hand side of the equation of delta YIT minus 1. that means of course that also yit minus c is going to be a relevant instrument for our endogenous regressor delta yit minus 1. However, take into account that the coefficient is different. We still get gamma minus 1, but we now multiply it with gamma. And because of the fact that gamma is in between 0 and 1, that means of course that this coefficient generally is smaller than the coefficient that we had with respect to yit minus 2. What does this mean? Well, that means that yit minus c still is a relevant instrument, but the relevance is actually weaker than what we had with respect to yit minus 2. Well, we can of course go on, and we could also now substitute in the value for yit minus c. Then of course what we're going to get is gamma times yit minus 4 plus vi plus wit minus c. If I'm going to do that, then the most important term is of course this first term that we have over here, and we are going to see that indeed there is a relationship between yit minus 4 and delta yit minus 1, because of the fact that we do see that, well, again, yit minus 4 is at the right hand side of the, say, equation of our endogenous regressor delta yit minus 1. However, again, the coefficient is going to be changed. It's now equal to gamma minus 1 times gamma squared. That means another time that this coefficient is going to be smaller than the coefficient that we had with respect to yit minus c, and it's also going to be smaller than the coefficient of yit minus 2. So therefore we are going to see that actually the strongest instrument that we have in general is going to be yit minus 2. And the more legs we are going to introduce, well, the, say, weaker the instruments are going to be. And that implies, of course, that at the moment that we're going to introduce, well, longer and longer legs into the set of instruments, that we're only going to introduce then, say, many weaker instruments. And therefore, it is very recommendable, and in contrast to what I have said so far, it is recommendable to not introduce all the different legs, so not to use all the potential moment restrictions that we have in our analysis. It is better to only use a couple of different legs. So for example, it is better not to use all the legs, but for example only use yit minus 2, yit minus c, and, well, eventually also yit minus 4, and not to use any higher order legs. And the reason why you should do that is because of the fact that this reduces a small sample bias of IV estimation due to many and weak instruments. We do already know that IV estimation, even though it's a consistent estimation method, that means that at the moment that we have many observations, well, then we do know that IV estimation is correct. However, at the moment that we have fewer observations, then at that moment in time there is a so-called small sample bias. IV will actually have a bias at the moment that we do not have that many observations. And that small sample bias is going to be larger at the moment that the instruments are going to be weak, or at the moment that we have many instruments. So therefore, at the moment that we are going to introduce fewer instruments, and we're only going to introduce the strongest instruments that we have, such as yit minus 2 and yit minus c, then at that moment in time the small sample bias is going to be reduced. However, we should take into account that there is one special case, and that is a situation in which gamma becomes close to 1. Well, gamma can never be exactly equal to 1, but suppose that gamma is exactly equal to 1, so then we have the, well, special case of a unit root. Well, then at that moment in time, you realize that then the relationship between delta yit minus 1, we do of course know that that's equal to gamma minus 1 times yit minus 2 plus vi plus wit minus 1. Well, if I substitute in here gamma equal to 1, then the first part over here is going to be completely deleted. And that means that then the delta yit minus 1 is simply equal to vi plus wit minus 1. Well, that means of course that an important part of the relationship between delta yit minus 1 and yit minus 2 is going to be completely dropped out, because of the fact that no longer yit minus 2 is here directly at the right hand side of the equation of delta yit minus 1. Take into account, by the way, that unlike what actually might be suggested by this equation that we've over here, yit minus 2 has still some relevance. It's a weak instrument, but it still has some relevance. And the reason behind that is because of the fact that we should take into account that, well, yit minus 2, of course, is also affected by this vi that we've over here. However, that is really of a second order relationship, and that means that at the moment that gamma is going to be close to 1, then all lagged values and instruments are weak. Then even using yit minus 2, as in Anderson and Chow, does not work then very well. I would like to illustrate this based on a simulation, and therefore again we are going to use our model yit is equal to gamma yit minus 1 plus vi plus wit, and I'm going to assume that both vi as well as wit, they're normally distributed with 0 means, and the variances are going to be equal to 0.1 for vi and 0.5 for wit. In addition to that, I'm also going to assume that t is equal to 20, so the number of time periods is equal to 20, and n is going to be either equal to 50, that is, I would say, the small sample case, or it's equal to 500, that is, in the case of a larger sample. I'm going to assume that the values of gamma, they actually range from 0.25 to 0.5, 0.75, 0.9 and 0.95, and take into account that these last two cases, of course, are already very close to a unit root. Then we're going to estimate gamma, first of all by using within estimation or fixed effects estimation. I'm also going to use Ariane bond, and I'm going to do that in two ways. First of all, I'm going to use only two legs, so only yit minus 2 and yit minus c, and I'm going to use Ariane bond using 9 legs. And even though that doesn't look like a lot of different legs, you should take into account that in that particular situation we're going to use 36 different instruments. Well, at the moment then we are going to look at our results. Then we do see that, first of all, at the moment we're going to look at the fixed effects estimator. That the fixed effects estimator generally is biased. We do see that actually all these values that we have over here, they're actually quite off from the target values that we actually want to have. And that is correct because of the fact that the fixed effects estimator in this case is not the correct estimator to use. Instead, we should use in this case Ariane bond, and as already said, we're going to look at two different ways to use Ariane bond. First of all, with few instruments, and we're going to also use the many instruments case. At the moment that we're going to look at few instruments, then we do see that, well, at least at the moment that gamma is not too large, then we do see that we do actually do quite well. We see that we do even still a little bit better in the case that n is equal to 500. We are a little closer, and also with smaller standard errors. But even in the case that n is equal to 50, we do actually quite well. Then at the moment that gamma becomes equal to 0.9, we still actually do quite well. But we do already see that there's going to be a little bit of a larger bias at the moment that n is equal to 50. However, at the moment that gamma becomes equal to 0.95, then we don't do so well anymore. Especially at the moment that n is equal to 50, then we are quite off from the target value of 0.95. We get a lot closer, of course, at the moment that n becomes equal to 500, but still we are somewhat off from our target value. At the moment that we're going to look at the many instruments case, then at the moment that we're going to look at here at very low values, gamma equal to 0.25 and gamma equal to half, then we still see that we do actually quite well, but especially in the case that n is equal to 50, we are somewhat further away from our target values than what we had at the moment that we only used, say, two different legs. At the moment that gamma is equal to 0.75, then we do already see somewhat of a bias at the moment that we have, say, our small sample case. Still, the large sample case is not really a problem. At the moment that gamma becomes equal to 0.9, then we do see actually that we have a larger problem here. Even in the larger sample case, actually we do see that we are somewhat off from our target value. And we do actually quite bad at the moment that gamma becomes equal to 0.95, and we do see that the difference is quite somewhat larger than the difference that we had at the moment that we only used a few different instruments.